Hi everyone. In this lecture, we are going to be discussing a variety of concepts which relate to blockchains, such as signatures, keys, and transactions. Now, a lot of the content that we'll be discussing is inspired by Bitcoin. And the reason for this choice is that Bitcoin is the pioneering blockchain network that we know of. So, a lot of those concepts you see will be directly related to how Bitcoin implements these concepts. So, as we look into blockchains, the first thing we should be discussing is the motivation behind, creating blockchains. And primarily, the motivation behind creating Bitcoin was to allow non-trusting entities to transact with each other without a third party being necessary. So, in the real world, whenever we have a transaction, to make sure everything in the transaction goes smoothly, we typically make use of a third party, such as a bank. So what the bank does is when money is being paid from, say, a sender to a receiver, the bank checks if the money is valid. The bank checks if the receiver and the sender are all legitimate entities, and also the bank makes sure that things like double spending do not happen. Double spending is a phenomenon where people try to spend the same money twice. All those sorts of things are ensured by a third party, which ensures that the transaction goes smooth. Blockchain, and specifically Bitcoin, was created with the motivation that we would eliminate this need. We will be showing how this need has been eliminated with the use of blockchains. Basically, the challenge that we have here is we want to establish trust in an environment where nobody trusts each other. And so to do so, what Bitcoin suggested was to create a verifiable ledger. By ledger, we mean a history of transactions, which is replicated across every node in the blockchain network. Because this ledger is replicated everywhere, and because we have a system which we will show, which ensures that all of these ledgers are consistent, that is to say, they say the exact same thing, we have a way in which we can create trust. So moving forward, an account in a blockchain setting, or specifically a Bitcoin setting, is basically a pair. It is a pair of a public key and a private key. And the address of an account, when we say the address, when we say the Bitcoin address or the blockchain address of an account, we basically mean some form of the public key. So the public key might go through a hash, and that hash can be referred to as an address. So basically, it's a derivation of the public key. And in the context of Bitcoin, whenever we say transaction, what we do is by saying we have a transaction, what we're basically doing is we're creating a transaction which contains an amount, which is how many Bitcoins, or in other sorts of cryptocurrency networks, how many Ether or something like that. And we also specify within that transaction the address of the receiver, whoever is receiving the money. And remember, we said the address is a derivation of the public key. So basically, in a way, we put in the public key of the receiver along with the amount of money that they're going to receive. And we sign this whole transaction with the private key of the sender. Now, this specific bit is very important. We will explain why, but just keep in mind that we need to sign it with the private key of the sender. This transaction that we will create will also reference all the previous transactions which gave this money to the sender to begin with. So if the sender is giving some Bitcoins, those Bitcoins must have been acquired by the sender in some fashion through some transaction. Someone must have sent those to the current sender. So it should also reference those previous transactions. So in this way, because every transaction is referencing the previous transaction, you can walk through this chain of transactions to trace back the ownership history of those transferred Bitcoin all the way back to the beginning of that Bitcoin, of the creation of that coin. So so two important details. Firstly, the transaction contains the amount and the public key of the receiver, and that it is signed with the private key of the sender, and also that the transactions refer previous transactions. Now, Bitcoin or blockchains also use a concept known as public key cryptography. So we've been talking about public and private keys, and the important detail here is that the public and the private key are mathematically related. So if something, since the transaction contains the public key of the receiver, because of this public key cryptography property, only the private key of the receiver can decrypt that transaction and provide access to those Bitcoins. As we discussed earlier, we have two important functions, which is the sign function and the verify function. So when you sign, you sign with a private key, you sign a message with a private key, and this gives you a signature. Later, if you want to verify, you would have to use the corresponding public key that is related to that private key to verify that signature. So in this way, this cryptographically related private and public keys allows for the sign and verify functions, which we've already discussed in the hash functions lecture, but we will be seeing more of this now. This is another view of transactions, and so we can think of transactions as inputs and outputs. So here in this transaction specifically, we can see that in transaction F4184F, the transaction in the middle here, this transaction has received 50 bitcoins. So what this transaction can then do is it can create two new transactions, one for 10 bitcoins and one for 40 bitcoins, and then these two transactions can then later be claimed by a future transaction. So you can see this chain of transactions here. Yeah. So this transaction refers to this previous transaction. This transaction refers to this previous transaction. And so basically you can see how the bitcoins are passed down from one transaction to another, and then they're distributed to future transactions. So these 50 bitcoins eventually get split up. These 50 bitcoins are taken in as the input, and then they're split up as outputs. So 10 bitcoins goes to this transaction, is claimed by this transaction, and 40 goes here. So this is how we can view transactions, as a set of inputs and outputs containing the amount of bitcoins and also the addresses, as you can see under the sign function. So to sum up our view of transactions so far, let's take a look at this image. So in this image, you can see a couple of transactions. Now this might look confusing at first, but let's go through this one by one. So let's take the center image here, the center transaction here, and try to make sense of it. So if you remember from the previous slides, what does a transaction have to contain? So let's go back to the previous slide here. A transaction must contain the amount, of course, that will be sent, but more importantly, what are the important technical details that the transaction has to contain? It has to contain the address of the receiver, so the public key of the receiver, and this transaction must also then be signed with the private key of the sender. So if we go back to the image here, and if you look at the transaction in the middle, so to start to interpret this, first note that this is the transaction that sends money from owner 1 to owner 2. So owner 1 is the sender and owner 2 is the receiver. Now let's interpret this transaction top down. First, we have the public key of owner 2. So this is the address of owner 2. So remember, we said that a transaction must have the address of the receiver as the public key, of course. So it must have the public key of the receiver. So we have owner 2's public key here. And then it must also reference the hash, or it must also reference the previous transaction. So if we go back to the slide here, this transaction also references the previous transaction which provided the bitcoins to the current sender. So what we're going to do is we're going to take the public key of the receiver, and we're also going to take the previous transaction that we have here, and we'll hash them together. And lastly, we need to sign it with the private key of the sender. So this forms one full transaction. And as you can see, this transaction refers to the previous transaction. And again, the next transaction, when owner 2 will be giving the money to owner 3, will also refer to this transaction. So you can see a chain of transactions going here, and you can see how these are linked. Each transaction contains a hash of the previous transaction, as well as public keys and the signatures. So yeah, this summarizes our view of transactions. Moving on. We then discuss, again, this might be specific to the Bitcoin network or certain networks, but it's also an important detail that we should put out. Once transactions are signed and they're ready, they're sent to an area called the mempool, which is a waiting area for transactions. This can be thought of as local memory, or it can be global, of each of the nodes that are participating in the blockchain. So here transactions wait. They wait until a blockchain miner, we'll get into the details of what a miner does very soon. They wait until a blockchain miner verifies that this transaction is indeed legitimate. And to do so, they use the verify function that we just mentioned earlier. So we make sure that the signature in the transaction matches the public key of the sender. Remember that the transaction is signed with the private key of the sender. So you can use the public key of that sender to verify that this is indeed coming from that sender, since the public and private keys are related. What this does is it ensures that whoever is sending the money is indeed actually sending the money, and not someone else claiming to be that sender and sending money to themselves, or stealing money from a sender. So that is why the verify function will return true only if the public key matches the associated private key of the sender, which was used to sign the transaction. Now, one of the big issues that any transaction system or any currency system or any sort of system in which an exchange happens is to ensure that the double spending attack doesn't happen. So we discussed this briefly previously. So basically what this means is the same coin cannot be spent twice simultaneously to do different things. This would give someone unlimited spending power and would ruin the entire system. So this is called the double spending attack. And this is an issue that can very easily happen in the blockchain network that we've discussed so far. So for example, suppose two different transactions are being signed, and both of those transactions use the same bitcoins from a specific sender. However, since this is a network and nodes are spread across this network, different nodes might receive different transactions. So one node might receive a transaction with that money being sent somewhere, and another node might receive a transaction with the same money being used for something else entirely. So these two transactions are in conflict, which is to say they are disagreeing with each other, and they're featuring the same coins. So of course we have a double spending attack here. So we need to have a way in which we can get around this double spending attack. So a possible solution to the issue we've just been discussing in terms of transactions being in conflict with each other is the concept of blocks. So what do we mean? So instead of just collecting transactions and then broadcasting those transactions, what we're going to do is every node is going to tentatively commit the transactions that they receive. So the node is listening for transactions, they get a transaction, and they store it in their internal memory. And what the node is going to do is it's going to collect transactions that it receives, and it's going to group them together until you get, say, a certain number of transactions, and then it's going to group all of these transactions into an entity called a block, and then it's going to broadcast the whole block. And then other nodes, that when they receive this block from another node after the block is broadcasted, they will roll back their own transactions and take that block as the truth, and they will include that block in their local blockchain. They'll commit all those transactions that are part of that block. Now all the nodes will agree on the order of transactions, because whoever has emitted the block is dictating what the real order of the transactions are. So there is only one transaction that's going on. However, there is a clear problem here, because the blocks here are being dictated by the node that is emitting it or broadcasting it. So there's clearly a race of sorts, because different nodes are at the same time creating their own blocks, and all of those blocks may be perfectly valid. So whose block is going to be the block that gets to enter the blockchain? Because as we said earlier, the whole concept of a blockchain is everyone has to agree on the history of all the transactions that have occurred. So if different nodes are making their own blocks, that leads to a conflict of what block actually gets to be on the blockchain. This is basically the same issue that we've been discussing earlier with the transactions, but only on the block level. However, at the block level, we have a way to work around this. So there is a way to systematically determine who gets to create the block. And the solution that Bitcoin implements for this is a concept called proof of work. So what proof of work does is it creates a challenge for each node, and whoever completes that challenge successfully will be the one that gets to impose their block on the entire blockchain. So let's look into this. So for the proof of work, basically it's a game of guess the number. So what you're going to have to do is there's a number called unknowns. So this is a number that when hashed gives us a specific target value. This target is what is given out as a challenge. Basically, we want a target number of 0 bits in the hash. So hashing techniques, for example, like SHA-256 that we've discussed earlier, these are one-way functions. So basically, it's impossible to guess what sort of number you would need for us to give the output that we're looking for. So basically, you would have to scan all the possible values, the space of all possible values at random. Um, and then you'd have to come up with that one value that gives you the targets you're looking for. However, if you do have the supposedly correct answer, which when hashed will give you that target, it's very easy to verify. You just put it through the function and it gives you that value. So as a result of which, this whole thing is gamified. And so what these nodes have to do is they have to basically guess this number by linearly scan or some sort of random scan through the space of values until they reach that target. Now, whoever reaches that target first, whoever gets that value, which when hashed gives you the correct target, has won that proof of work challenge. As a result, they get to impose their view or their block in the entire blockchain. As a result, whoever is solving this first gets to make that imposition. Nodes that solve this proof of work, they attach that nodes that we discussed earlier to the block header, and they announce that block to the whole network. Everyone else can verify that this node has indeed correctly solved the problem because they can simply put that nodes through the hash function to check if it is indeed solving the target. And other nodes accept this block, and they include this block into their blockchain, and this process continues over and over again. Whichever node solves this problem first is rewarded for solving the problem, and often they will receive something like Bitcoins for their effort, or Ethereum on the Ethereum network, or it can even be in terms of transaction fees. So there is some sort of reward mechanism for solving the proof of work, and this gives an incentive for miners to mine. So these miners are basically the people who solve the proof of work problem, so that they get to attach their own block to the blockchain, and this is the incentive mechanism for those miners. And therefore, we have a chain of blocks now. So a chain of blocks such as this, each of which have been created by a miner solving the proof of work, is called a blockchain. And because we have a race going on where miners are struggling to find the proof of work fastest, whoever solves it first imposes that block. Everyone else accepts that block, and then the next block will be built on top of this block. And because everyone agrees to the rules of the game, all of the blockchains should hypothetically look exactly the same on each node. We will show later how this might not be always the case, as we can have blockchain forks. But generally, the idea is because everyone agrees on the rules, everyone should have the same blockchain replicated across all nodes that are participating in that blockchain. The first block in that blockchain is often called the genesis block. So basically, suppose you have a blockchain of a certain length, and from the last blockchain, each block in the blockchain will reference the previous block, and you can go through this chain all the way until the first block, which is called the genesis block. In this way, the entire transaction history of the system is maintained. You can look at this image to give you a good idea of what these blockchains or what the blocks in the blockchain look like. So they have the previous hash of the history of the blockchain. They also have the nonce value that we mentioned earlier, and they also have these transactions in each block.